Okay, so this time our topic is about first come first serve. Okay. So FCFS is an operating system scheduling algorithm that automatically execute queued requests and process in order of their arrival. So it is the easiest and simplest CPU scheduling algorithm. In this type of algorithm, processes which request the CPU first get the CPU allocation first. And this is managed with the FIFO queue, no, or the first in, first out queue. So the full form of FCFS is the first come, first serve. As the process enters the ready queue, its PCB or process control block is linked with the tail of the queue, and when the CPU becomes free, it should be assigned to the process at the beginning of the queue. So this will be the characteristics of FCFS as what we discussed last meeting. So an example of FCFS scheduling in a real-time example, in a real-life example of the FCFS method is buying a movie ticket on the ticket counter. In this scheduling algorithm, a person is served according to the queue manner. So the person who arrives first in the queue first buys the ticket, and then the next one. This will continue until the last person in the queue purchases the ticket. Using this algorithm, the CPU process works in a similar manner. Okay, here's the example of the first come first serve scheduling. So by far the simplest CPU scheduling algorithm. The process that requires the CPU first is allocated the CPU first, as I mentioned. So I will share to you the discussion of Anesto Academy related to the first come first serve scheduling. The simplest CPU scheduling algorithm. So it is easy to
understand that first come first served scheduling means the process that requests the CPU first is allocated the CPU first. That means whoever comes first will be given the CPU first. So the first process that requests the CPU will be given the CPU. And then the second process will be given the second chance. The third process that comes will be given the third chance, and so on. So it is fairly a very simple method that can be followed, and it is also a very simple method that can be implemented, and also it is a simple method to understand. So the implementation of the FCFS policy, or the first come first serve policy, is easily managed with a FIFO queue. So FIFO stands for first in first out. So this is a normal method that we follow in a normal queue. So what we mean by first in first out is the element that comes in first will be the element to go out first. That means the element that comes in first will be the element to complete its work and go out first. So it is very similar to the normal queue that we have in our day-to-day life. So think of this simple example where you are standing in a queue in order to pay your bills or something like that in front of a counter. So what happens is the person who comes first will be the one who will be given the chance to perform the activity first. So let's say that suppose this queue is for paying some kind of bills. So the person who comes first will get the first chance to go into the counter and pay the bill. And the second person will be given the second chance, and so on. So whenever a new person comes, he has to stand at the end of the queue or at the tail of the queue. And then this pattern is continued. So if you are following a very fair kind of queue, then a person who comes at the end will never be given a chance to go in first, or will never be given a chance to come in between any of the other members. He has to stand at the end of the queue. And also, if you are following a really fair queue, then whoever is standing in queue has to follow that pattern. Nobody will be allowed to take the chance until his chance arrives. So let's say that there are some old people standing or some children standing, and if you are having a fair queue, they will not be given a chance to go into the counter until and unless their chance arrives. You cannot break this queue. So I am taking this example because in this first come first served scheduling, this is what is going to be exactly followed. So keep this in mind. And as I told you, FCFS policy is easily managed by a FIFO queue. So this is an example of a FIFO queue where elements are queued up like this, and then the first element is known as the head of the queue and the last element is known as the tail of the queue. So when the head of the queue, which is this element, completes its execution and goes out, then this element over here will become the head. And if some other elements come in, then they will be added to the tail of the queue. That means they will be kept over here and that element will become the new tail. So that is how a FIFO queue is followed. And by making use of this FIFO queue, this FCFS policy can easily be implemented because it is going to follow a first come first served basis. So what happens is when a process enters a ready queue, its PCB is linked onto the tail of the queue. So we have studied about the different states that a process can be in, and we know that when a process is ready to be executed, it will be in the ready queue. And when it is in the ready queue, its PCB, that is a process control block, will be linked to the tail of the queue if we are following a first come first serve scheduling. And then when the CPU is free, it is allocated to the process at the head of the queue. That means here we have a queue where the processes are queued up like this, and then they are all waiting for the CPU. So when the CPU is free, the process which is at the head of the queue, that means this process will be given the CPU for its execution. And then the running process is then removed from the queue. That means once this process gets the CPU, then this process will be removed from this queue because it has already got the CPU for its execution. So this process will be removed, and this second process over here will be the new head. And then if some other processes come in again, they will be added to the tail, and that will be the new tail. So that is how first come first served scheduling works. Now let us see if this first come first served scheduling is an efficient scheduling or not. So here it says that the average waiting time under the FCFS policy, however, is often quite long. So if we are following a first come first serve scheduling policy or scheduling algorithm, then the average waiting time for each process is quite long. So let us see why that is by taking an example. So here let's consider the following set of processes that arrive at time 0. So here we have three processes P1, P2 and P3 that arrive at time 0 and wants to use a CPU for its execution. And then the burst time indicates the time that the process will take to complete its execution. That means the time it needs to hold the CPU for itself to complete its execution. So the process P1 has a burst time of 24 milliseconds, P2 has a burst time of 3 milliseconds, and P3 also has a burst time of 3 milliseconds. Now if the processes arrive in the order P1, P2, P3 and are served in FCFS order, then we will get the result shown in the following Gantt chart. So here let's say that the processes arrive in this order P1, P2, P3. That means P1 is the first process to arrive, followed by P2 and then P3. So if they arrive in this order and we are using the first come first served scheduling algorithm, then we will see the result shown in this Gantt chart, in which it shows the waiting time for each processes and the time each processes take for executing in the CPU. So if you see here, process P1 was the first one to arrive. So it did not have to wait any amount of time. So it is 0 and it took the control of the CPU. So P1 is executing in the CPU. And how long will P1 execute? It will execute for 24 milliseconds because that is the burst time for process P1. So it will execute for 24 milliseconds. And during the execution of P1, P2 is already waiting in queue because P2 was the second one to arrive. And P3 is also waiting behind P2. So how long did P2 have to wait? P2 had to wait 24 milliseconds because P1 took 24 milliseconds to complete its execution. And once P1 completes its execution and frees the CPU, then P2 will get hold of the CPU. And how long will P2 execute? It will execute for 3 milliseconds. So P2 executes for 3 milliseconds and meanwhile P3 is waiting in the queue. So how long did P3 wait? P3 had to wait for 27 milliseconds. Why is that? Because P1 took 24 milliseconds, Then the next chance was given to P2, which took 3 milliseconds. So 24 plus 3 equal to 27 milliseconds. So P3 had to wait 27 milliseconds. And once P3 gets the CPU at the 27th millisecond, it does its execution in the CPU and it spends 3 milliseconds in the CPU, thus showing this last time in the Gantt chart as 30 milliseconds. So this is what happens in a first come first serve scheduling algorithm if the processes arrive in the order P1, P2, P3, and these are the burst times. So as I said, the waiting time for P1 was 0 milliseconds, for P2 it was 24 milliseconds, and P3 was 27 milliseconds. So what is the average waiting time? It is 0 plus 24 plus 27 divided by 3, because 0 is the waiting time for P1, 24 is the waiting time for P2, 27 is the waiting time for P3, and total there are 3 processes. So we are adding up these values and dividing it by 3, and hence we get 17 milliseconds. So the average waiting time for this particular scenario when we followed first come first served scheduling algorithm is 17 milliseconds. Alright, now let's take another example. Now let's say that the same processes with the same burst time arrive in a different order. So let's say if the processes arrive in the order P2, P3, P1, however, the result will be shown in the following Gantt chart. So here in this chart, we are having the time each process takes and has to wait if they come in the order P2, P3, and P1. So remember that the burst time is the same like the previous example. P1 has a burst time of 24 milliseconds and P2 and P3 has burst times of 3 milliseconds. So here what happens is they arrive in this order P2, P3, and P1. So P2 is the first one to arrive, so it did not have to wait, and it takes control of the CPU and executes for 3 milliseconds because the burst time of P2 is 3 milliseconds. Then the next one that arrived was P3, which was waiting in queue. So how long did it have to wait? It had to wait for 3 milliseconds because P2 was executing for 3 milliseconds. So at 3 milliseconds, P3 gets hold of the CPU, and that P3 also executes for 3 milliseconds because the burst time of P3 is 3 milliseconds. And meanwhile, P1 is waiting in queue because P1 was the next one to arrive after P3. How long did it have to wait? We see that P3 completes its execution at the 6th millisecond because the execution time for P3 is 3 milliseconds. So total how much time did P1 have to wait? It had to wait 6 milliseconds because P2 took 3 milliseconds and P3 also took 3 milliseconds. So total of a 6 millisecond P1 had to wait. And then at the 6th millisecond, P1 got hold of the CPU and it does its execution up to the 30th millisecond because the burst time of P1 is 24 milliseconds. So in this case, let us see what is the average waiting time. So in this case, as I said, the waiting time for P1 was 6 milliseconds as we see here, and the waiting time for P2 was 0 milliseconds because it was the first process to arrive, and the waiting time for P3 was 3 milliseconds because it was the second one to arrive and P2 took 3 milliseconds. So here if we calculate the average waiting time, it is 6 plus 0 plus 3 divided by 3. So if we calculate here, it comes out to 3 milliseconds. So we see that in this case, the average waiting time for the processes has reduced substantially. In the previous example, we saw that it was 17 milliseconds for the same processes, but in a different order. So we see that depending upon the order in which they arrive and depending upon their burst time, the average waiting time in case of a first come first served scheduling algorithm varies greatly. So this reduction is substantial. Thus, the average waiting time under an FCFS policy is generally not minimal and may vary substantially if the process's CPU burst time vary greatly. So this reduction that we saw in these two examples is a great reduction. That means there is a great difference between the first and the second example. The average waiting times were really different. 17 and 3 has a great difference between them. So the average waiting time in this is not minimal generally, and it may vary substantially depending upon the burst times of the processes and the order in which they arrive. And also the next thing that we have to remember is The FCFS scheduling algorithm is non-preemptive. So we have already discussed about preemptive and non-preemptive scheduling. So when a process is executing in the CPU, if that process can be stopped by some other process, and if some other process can get the CPU while the previous process was still executing, then that is called a preemptive technique. But when one process is in hold of the CPU and the CPU cannot be taken away from it until and unless that process completes its execution or waits for an IO, then that is known as a non-preemptive technique. So the first come first served scheduling algorithm is non-preemptive. That means if a process gets the CPU, then all the other processes have to wait until and unless that process either completes the execution or waits for an IO. So that is why I took the example of that queue in our day-to-day life. So until and unless the person who is at the counter finishes his work, no other person can come and interfere in between. So only when he finishes his work in the counter and goes out of the queue, the next person in queue will get the chance. So FCFS scheduling algorithm follows the same policy. So that is what is written here. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU either by terminating or by requesting IO. So this is what I just explained. Now the problem with this FCFS scheduling is that the FCFS algorithm is thus particularly troublesome for time sharing systems where it is important that each user gets a share of the CPU at regular intervals. So if you are having a time sharing system where each process needs to get the CPU at regular intervals of time, it is not going to be possible in this FCFS algorithm, because only when one process completes its execution completely or goes to a waiting for IO state, then the CPU can be given to some other process. So until that, no other process can take control of the CPU. So if a process is having a very big burst time, let's say that there is a big process with a big burst time, that means it needs a huge amount of time to complete its execution in the CPU, then what will happen? Until and unless that process completes its execution, all the other processes in the queue will be waiting and starving for the CPU. They will not get it until and unless that big process completes its execution. So it would be disastrous to allow one process to keep the CPU for an extended period. So this will not be a very good technique, because let's say that we have so many small processes which needs very less amount of time to complete, but at the head of the queue there is a big process that needs a big amount of time to complete. Then until and unless that big process completes its execution, all the other processes, though they may have a very less burst time, will have to wait. So that is the bottleneck here. So if you are having some big processes, that means processes needing more time, then they are going to delay the entire processes that are waiting in the queue. So this is the disadvantage of this FCFS scheduling algorithm. So FCFS scheduling algorithm is very easy to understand and easy to implement, but it is not an efficient algorithm. So this is the first CPU scheduling algorithm that we need to know about. And moving on in the following lectures, we will be seeing more CPU scheduling algorithms which may be better than this and which may be having more advantages as compared to this FCFS scheduling algorithm. So as a basic, this is the first algorithm that you need to know about, and I hope this was clear. From this lecture onward,
Okay, so this will be an additional example from NESO Academy. So a while ago, we discussed about the advantages of using the first come first serve scheduling. So to continue with another example for the first come first serve scheduling, we use this video from NESO Academy.
higher burst times arrive before processes of smaller burst times, then the processes of smaller burst times will have to keep waiting for a long time until the processes of higher burst times complete their execution. Now this is known as the convoy effect. So if processes with higher burst time arrived before the processes with smaller burst time, then smaller processes have to wait for a long time for longer processes to release the CPU. So this is what I just explained. And this disadvantage that we have is known as the convoy effect. This effect in which the smaller processes keep waiting for the longer processes to release the CPU is known as the convoy effect. Alright, now keeping all this in mind, let us go to the problem and see what is the problem and how can we solve the problem. So here is the problem. Consider the set of 5 processes whose arrival time and burst time are given below. So we have a set of 5 processes whose process IDs are P1, P2, P3, P4 and P5. And here it is given the arrival time and here is given the burst times of these 5 processes. Now the question is, calculate the average waiting time and average turnaround time if first come first served scheduling algorithm is followed. So what we want to do here is that if FCFS scheduling algorithm is followed here, we have to calculate what is the average waiting time and what is the average turnaround time for these 5 processes. So when we discussed about the scheduling criteria, we have already defined and described what turnaround time and waiting time means. So we have to calculate the average waiting time and average turnaround time. So let us see how we can do this. So in order to solve this, first of all, we need to prepare the Gantt chart for these 5 processes. Now let us see how will the Gantt chart of these 5 processes look like. So coming to the solution, here I have shown the Gantt chart for these 5 processes that we have. So basically what a Gantt chart does is that it will show you when did a particular process get the CPU for its execution and when did it complete its execution. So from this we can understand and see that. So let us see. So here if we analyze this table, we see that P3, the process P3 arrived at time 0. So this was the first process to arrive. So we are following FCFS scheduling algorithm, which is first come, first served. So the process that comes first must be served first. So P3 is the one that arrived first as it arrived at time 0. So P3 gets the CPU and it's doing its execution in the CPU. Now, how long does process P3 use the CPU? For that, we need to see the burst time of process P3. So we see that the burst time of process P3 is 3 units of time. So the process P3 will be executing for 3 units of time. So that is why we have shown this 3 over here. It arrived at time 0 and it got the CPU at exactly time 0 and then it executed for 3 units of time, and hence the completion time of P3 is 3 unit of time, which is shown here. Now if you see here, next we have a blank or a shaded box. So the shaded box represents the idle time of the CPU. Now why do we say that this time is idle? So in order to find that, we have to see this Gantt chart and this table. Now if you look at this Gantt chart, here in the chart we see that at the 3rd unit of time, P3 completed the execution. Now if you look at this table, there are no processes that arrived at the 3rd unit of time. If you check the arrival times, you see that no processes arrived at the 3rd unit of time. So at the 3rd unit of time, when P3 completed its execution, the CPU is idle. It is free and it was sitting idle. Nobody was using the CPU. Now if you look at this arrival times again, after this 3 where P3 completed, what is the next arrival time that we have? It is 4. 4 is the next biggest number just after 3. And which process is that? P1. So P1 arrives at the 4th unit of time. So at time 4, P1 arrived and it got the CPU for its execution. So here we see that from time 3 to 4, nobody arrived. So that is why this portion is shaded and left blank, because this is the idle time of the CPU. Okay, now let's see. Process P1 arrived at time 4, alright, and what is the burst time of process P1? It is 5 units of time. Now remember that burst time means the time that a process needs to use the CPU for its execution. We have already discussed that. So P1 will execute for 5 units of time. So here P1 at the 4th unit of time got the CPU and it will execute for 5 units of time. So 4 plus 5 gives us 9. So the completion time of P1 is 9 unit of time. So at the 9th time or the 9th unit of time, P1 completed its execution. Now let us see which is the next process that is going to get the CPU. So we finished P3, we finished P1. Now if you see, P1's arrival time was 4. So what is the next unit of time that we have that is just greater than 4? If you look, it is 5. And which is the process? Process P5. So it arrived at the 5th unit of time. But if you look at the Gantt chart, we don't see any 5 over here. And why is that? That is because even though P5 arrived at the 5th unit of time, at that time P1 was already using the CPU. The CPU was with P1 at that 5th unit of time. P1 was using the CPU up to the 9th unit of time. So exactly at P5 or exactly at its arrival time, P5 could not get the CPU and it was waiting for the CPU until P1 completed its execution. So once P1 completes, the next one to get the CPU is P5. So P5 got the CPU at the 9th unit of time when P1 completed its execution. Now if you see what is the burst time of P5, it is 4 units of time. So P5 will execute for 4 units of time, that is from the 9th unit of time plus 4, which will give us 13. So 13 is the completion time of P5. Now which is the next process that will get the CPU? So if you look at the arrival times, P5 was the one that just completed now. Now what is the process that arrived after P5? We see that there is 6 and again 6 here. That means both processes P2 and P4 arrived at the 6th unit of time. Now the question arises, since they both arrived at the same time, who will get the CPU? So in most of the systems, what they follow is that when two processes arrive at the same time, then the process with the smaller process ID will first get the CPU in case of FCFS scheduling algorithm. So if you look here, P2 and P4 both arrived at the 6th unit of time. Now who will get the CPU? The process with the smaller process ID. Here P2, 2 is less than 4. So P2 will be getting the CPU. So P2 got the CPU over here at the 13th unit of time when P5 just completed. And how long will P2 execute? P2 will execute for 4 units of time. So 13 plus 4 is 17. So P2 completes its execution at the 17th unit of time. Now what is the next one? Obviously it is P4, which is the last one, and P4 gets the CPU after P2 completes. And how long does P4 execute? It executes for 2 units of time. So 17 plus 2, which is 19. So P4 completes its execution at the 19th unit of time. So this is what we can see from the Gantt chart, and this is how you should be forming a Gantt chart for a particular set of processes according to the algorithms that they follow. Alright, now our question was to find the average waiting time and the average turnaround time. Now let us see how can we proceed and find out these two values. Alright, so here I have just made that table which we saw before a bit smaller so that it fits on the screen. It's the same table, and here we are going to calculate the average waiting time and the average turnaround time for this set of processes that we have. So before we calculate, let us know what is the formula that we need to apply to calculate the average waiting time and the average turnaround time. So first of all, the way to calculate the turnaround time is completion time minus the arrival time. So this is the formula that we need to apply to calculate the turnaround time of a particular process. The completion time, that means when it completed its execution, minus the arrival time, that means the time at which it arrived. So let us not memorize this formula, but let us try to understand how we arrive at this formula. So when we have discussed about scheduling criteria, we have discussed about this turnaround time. So what is a turnaround time? Turnaround time is the time that is required for a process to complete its execution from the time it first came to the ready queue until and unless it is completely finished or completely executed. So don't confuse it with the burst time. Burst time is a time that a process will take for its execution in the CPU, but turnaround time will include the entire time that a process takes to complete its execution. So that will include the waiting time when it waits for IO operations and all that. So turnaround time is the time that a process takes from the time it comes to the ready queue for the first time until and unless it completes its full and final execution, which includes all the time it waited for different things. So how do we calculate this? It is the completion time minus the arrival time. So completion time is the time a process completes its execution fully. So that includes the waiting time and everything. So for example, if we look at process P1, it completed its execution at the 9th unit of time. So that is the completion time for process P1. Now minus the arrival time. So when did process P1 actually arrive? So for that you have to look at this table here. So when did process P1 arrive? It arrived at the 4th unit of time. So the completion time, which is 9, minus the arrival time, which is 4, which is 5 unit of time, is the turnaround time for process P1. So that is how you calculate. So if you think of it, you can understand the completion time, that is the time that process took to entirely complete its execution, minus the time that it arrived. If you subtract this, you will get the turnaround time. All right. Now, what is the next thing that we need to calculate? It is the waiting time. So waiting time can be calculated like this: turnaround time minus the burst time. So waiting time is the time that a process spends waiting to get the CPU. Now, we already calculated the turnaround time. So turnaround time is the entire time that a process takes to complete its execution. And from that, if we minus the burst time, that means the time that a process actually needs for its execution in the CPU. That is the burst time. So from the entire time it took, if we just subtract the burst time, which is the time that a process should actually take if it was just given the CPU for its execution without being disturbed and without it having to wait for anything else, then we will get the waiting time. So even this, don't try to memorize it, try to understand what is it. So the entire time it takes minus the time it actually takes in the CPU, the burst time. If you subtract these two values, then you get the waiting time. Alright, now we know the formulas, and now let us try to apply this in this set of processes and try to calculate the average turnaround time and the average waiting time. So here we have a table in which we will calculate the required values. So here we have the process IDs P1 to P5, and here we have the completion time, and here we will have the turnaround time and the waiting time. So the completion times can be easily seen from the Gantt chart, and we fill up looking at the chart here. So the process ID P1, it completes at the 9th unit of time, so it is 9. And looking at P2, it completes at 17th unit of time, so it is 17. And P3 at the 3rd unit of time, and P4 at the 19th unit of time, and P5 at the 13th unit of time. So that is how we fill up this column for the completion time. I'm looking at this chart over here. Now we have to calculate the turnaround times and waiting times for these processes one by one. Alright, let's see. For the first one, process P1, how do we calculate the turnaround time? So what is the formula to calculate turnaround time? We have it here. So it is completion time minus arrival time. So what is completion time? It is 9 unit of time. And what is the arrival time of P1? The arrival time of P1 was 4 unit of time. So what will be the turnaround time? It will be 9, which is the completion time, minus 4, which is the arrival time, which is giving us 5 units of time. So that is the turnaround time for process P1. Now what is the waiting time? So the waiting time is turnaround time minus burst time. So here we already found the turnaround time, which is 5 units of time. And what is the burst time? It is again 5 units of time for process P1. So what is the waiting time? It is 5 minus 5, which is 0. So we got 0 here. So let us just observe at the Gantt chart. Why did we get 0 for P1? So when you look at P1 here in the chart, P1 was not the first process to arrive, but at the time P1 arrived, when did P1 arrive? At 4th unit of time. At the 4th unit of time, the CPU was actually idle. Nobody was using the CPU. So as soon as P1 arrived, it got the CPU for its execution. So that is why P1 did not have to wait for the CPU. It got the CPU exactly at the time it arrived. So that is why the waiting time of process P1 is 0. Alright, now let's come to process P2. So P2's completion time is 17, and what is the turnaround time? It is completion time minus arrival time, which is 17 minus what is arrival time? Arrival time of P2 is 6. So what will it be? It is 17 minus 6, which gives us 11. And what is the waiting time? So the waiting time is turnaround time minus burst time. So what is turnaround time? It is 11. And what is the burst time of P2? It is 4. So what does it give? It gives us 11 minus 4, which is 7. Now similarly for P3, the turnaround time will be the completion time, which is 3, minus the arrival time, which is 0. Now what is it? So it is 3 minus 0, which is 3. And what is the waiting time? Waiting time is turnaround time 3 minus the burst time. What is burst time of P3? It is also 3. So it will again give us 3 minus 3, which is 0. Now again, if you observe this in the chart, P3 was the first process to arrive, so it did not have to wait for the CPU. It was the first process to arrive, and we assume that the CPU was free at that time, so it arrived at the 0th unit of time and it didn't have to wait, so it got the CPU at that time itself, hence the waiting time is 0. Now let's do the same thing for process P4. For P4, the completion time is 19, and what is the arrival time? The arrival time of P4 is 6. So what will be the turnaround time? It will be 19 minus 6, which is 13. And what is the waiting time? The waiting time is 13, which is the turnaround time, minus the burst time of P4, which is 2. So that will give us 13 minus 2, which is 11. Now similarly for P5, the completion time is 13. So what is the turnaround time? It is 13, which is the completion time, minus the arrival time, which is 5. So that will give us 13 minus 5, which is 8. And let's see what is the waiting time. The waiting time is the turnaround time, which is 8, minus the burst time of P5, which is 4. So that gives us 8 minus 4, which is 4. So here we have calculated the turnaround times and the waiting times for processes P1 to P5 using this formula. Now the last step is to calculate the average turnaround times and the average waiting times for this set of processes that we have seen here. So now let's calculate the average turnaround time. It is very easy. We already have all the values here. It is 5 plus 11 plus 3 plus 13 plus 8 divided by 5. We are dividing by 5 because we are having 5 processes. So it gives us 40 divided by 5, which is 8 units of time. So the average turnaround time for this set of processes while they follow FCFS scheduling algorithm and when they arrive at the particular arrival time as given in the question is 8 units of time. This is the average turnaround time. Now similarly, the average waiting time can be computed here. The average waiting time is again 0 plus 7 plus 0 plus 11 plus 4 divided by 5. So it gives us 22 divided by 5, which is 4.4 units. So on an average, we have 4.4 units of waiting time. So the average turnaround time, that means the average time that a particular process takes to complete its full execution from the time it came to the ready queue for the first time till the time it completes its full execution is 8 units of time. And then the average waiting time, that means the average time a process spends waiting in this case is 4.4 units of time. So for this particular question, when the processes arrives at the arrival times as given to us in this question, this is the average turnaround time and the average waiting times that we get. So there may be other scenarios where processes with higher burst times have arrived before the processes of smaller burst times, and then the smaller processes end up waiting for a long time. So in that kind of scenarios, the average turnaround time and average waiting times will be much more than this. So as I told you, this FCFS scheduling algorithm, it is simple, but it is not very efficient because the average times that we calculate here can vary drastically depending upon when the processes arrives and what is the
Okay. So a while ago, we will give you an example of a first come first serve scheduling with the computations of average waiting time and turnaround time. So for you to understand better the first come first serve scheduling, this will be the second example of the first come first serve, also coming from NESO Academy.
we can solve it. So here is the problem. The arrival times and burst times of a set of 6 processes are given in the table below. So we have a table here where the arrival times and burst times for a set of 6 processes are given. So the processes are denoted with process IDs P1 to P6. So here is the question. If FCFS scheduling algorithm is followed and there is 1 unit of overhead in scheduling the processes, find the efficiency of the algorithm. So it says here that for this set of 6 processes, when they arrive at this times and when they have this unit of burst times, and if they are following a first come first served scheduling algorithm and there is 1 unit of overhead in scheduling the processes, we have to find the efficiency of this algorithm. Alright, so before we go into that, let us try to understand what does this term mean. There is 1 unit of overhead in scheduling the processes. So we already know how FCFS scheduling algorithm works. The process that comes first will be served first or given the CPU first. That's what we mean. Now, by this 1 unit of overhead in scheduling processes, what we mean is that when a process arrives in the ready queue and is to be given the CPU cannot be given just at that particular instant. That means exactly at that time, the CPU cannot be given to the process. the system has a delay, a slight delay of 1 unit before it assigns the CPU to each processes. So whenever a process arrives, the system will have 1 unit delay in assigning the CPU to the process. And even when the CPU is switched between processes, there will be 1 unit of time delay in switching the CPU between the two processes. So 1 unit of time delay will be there. So that is what we mean by 1 unit of overhead in scheduling the processes. So if it is like this, then what will be the efficiency of this particular algorithm for this particular set of processes if they arrive at this particular set of times and if they have this particular set of burst times? Let us try to find that out. So first of all, what we are going to do is we have to draw the Gantt chart for this. So let us see how we can form the Gantt chart for this set of processes following this method. So coming to the solution, we are going to form the Gantt chart, and this is how the Gantt chart for this set of processes will look like. So let me explain this Gantt chart to you. It looks a bit different from the previous Gantt chart that we have formed in the previous solved example that we discussed in the previous lecture. And why is that? That is because we are having this del in this Gantt chart. And what is this del? This del denotes the unit overhead in scheduling the processes. Because in the question we said that there is 1 unit of overhead in scheduling the processes. So that 1 unit of delay is denoted by this del over here in this Gantt chart. Alright, so let's see how we have formed this Gantt chart over here. So we see that processes P1 to P6, they arrived at this units of time. So P1 arrived at 0 unit of time, P2 at 1, P3 at 2, P4 at 3, P5 at 4, and P6 at 5. So the arrival times are 0, 1, 2, 3, 4, 5, and these are the burst times. So which is the first process that arrived? It is P1. It arrived at the 0th unit of time. So here we are following FCFS scheduling algorithm, which is first come, first served. So P1 should be the one that should be served first or given the CPU first. So here at the 0th unit of time, P1 arrives. But as we know that there is 1 unit of overhead in scheduling, as I told you, the CPU cannot be assigned directly at that time itself, but there will be a slight delay of 1 unit of time. So even though P1 arrived at 0 unit of time, there is a delay of 1 unit of time. So that is why we have shown this del over here. So from 0 to 1, that means for 1 unit of time, this del is shown, and exactly at time 1, P1 will get the CPU for its execution. So after this delay of 1 unit, P1 gets the CPU for its execution. Now how long will P1 use the CPU? The burst time. We have to check the burst time for P1. What is it? It is 3 units of time. So P1 will use the CPU for 3 units of time. So 1 plus 3 gives us 4. So the completion time of P1 is 4 units of time. Now again, if we look at the table here, we see that P2 arrives at 1, the time 1. So P2 should be the next one. So if you observe this table, it is 0, 1, 2, 3, 4, 5. So obviously the order of arrival is P1, P2, P3, P4, P5, P6. So it is easy to remember for this example. So P2 is the next one that should get the CPU. But as we know that there is 1 unit of overhead in scheduling the processes, again after P1 releases the CPU, before P2 gets the CPU, there will be 1 unit delay. So 4 to 5, there is this delay over here. Now at the 5th unit of time, P2 will get the CPU. And how long will P2 execute? It will execute for 2 units of time. So from 5 to 7, 5 plus 2 is 7. So P2 executes for 2 units of time and the completion time is 7. Now again, the next process is P3, but P3 will have to wait for 1 unit of time. So again, 7 to 8 is the delay, and then at the 8th unit of time, P3 gets the CPU and executes for 1 unit of time. So 8 plus 1 is 9. So P3 executes for 1 unit of time. And again, before P4 gets the CPU, there is a delay of 1 unit of time. So 9 plus 1 is 10. So there is this delay here. And when P4 gets the CPU, it has to execute for 4 units of time. So 10 plus 4 is 14. So P4 executes for 4 units of time. Hence the completion time is 14. Then again, before P5 gets the CPU, we have to wait for 1 unit of time. So it comes from 14 to 15. And P5 executes for 5 units of time. So from 15 to 20. 15 plus 5 is 20. So P5 uses the CPU up to the 20th time. And then again, there is a delay of 1 unit of time. So 20 plus 1, 21. And then lastly, P6 gets the CPU and it has to use a CPU for 2 units of time. So at the 21st unit of time, P6 got the CPU and it executes for 2 units of time. So 21 plus 2 is 23. So this is how we form the Gantt chart for this set of 6 processes when there is a unit overhead in scheduling the processes and when they arrive at this particular times with this particular burst times. So if we see the entire time it took for these 6 processes to complete execution was 23 units of time. Alright, so we have this information with us, and with this let us try to calculate the efficiency of this algorithm, and let's see how we can do that. So to find the efficiency of this algorithm, there are certain values that we need to first calculate, and let's see what they are. So the first one is the useless time or the wasted time. So we see that this del, which was the overhead in scheduling the processes, is the time that is wasted. That time was not being utilized by any of the processes, and it is the useless time or the wasted time. So how much time did we waste? We have 1, 2, 3, 4, 5, 6. So we have 6 units of del over here, and we already said that the overhead is for 1 unit of time. So all this del represents 1 unit of time. So 6 dels into 1 unit of time. Hence we have 6 units of time that is wasted or which was useless. And then next we have the total time that was taken for this entire processes to complete their execution. So if you look at the Gantt chart, it is 23. The last process P6 completed its execution at the 23rd unit of time. So the total time is 23 units. And then we have the useful time. So from these two values, we can calculate the useful time. So what is the useful time? The useful time will be the total time minus the useless or the wasted time. So the useful time will be 23 units, which is the total time taken by these processes to complete their executions, minus the useless time or the wasted time, which is 6 units of time. So that gives us 17 units. So the useful time is 17 units. Alright, so from this, now let us calculate the efficiency. So the efficiency will be calculated like this: useful time divided by the total time. The useful time that was spent divided by the total time that was taken. So what is the useful time? It is 17 units. And what is the total time that was taken? It is 23 units. So if we divide 17 by 23, we get 0.7391. And if we convert it to percentage, it is 73.91%. So this is the efficiency of this algorithm for this particular set of processes when they arrived at the particular given arrival times with the given burst times, and when there is a overhead of 1 unit of time in scheduling the processes, and when they follow the first come first served scheduling algorithm. So that is how you calculate.
Okay, so as what we have shown earlier regarding the computations of the first come first serve scheduling, so we have a different advantages of the first come first serve. So of course, the simplest form of the CPU scheduling algorithm and easy to program, and at the same time first come first serve. The disadvantages or the cons of the first come first serve, or here are the cons or drawbacks of of using first come first serve scheduling algorithm. So it is non-preemptive CPU scheduling. Also, so other of the process has been allocated to the CPU, it will never release the CPU until it is finishes executing. The average waiting time is high. So short processes that are at the back of the key or queue have to wait for the long process at the front of to finish, and not at an ideal technique for time sharing system. Because of its simplicity, first come first serve is not very evident. So again, first come first serve is an operating system scheduling algorithm that automatically executes queued requests and process by order to their arrival. It supports non-preemptive and preemptive scheduling algorithm. So first come first serve is the FCFS. A real example of the first come first serve method is buying a movie ticket on the ticket counter. It is the simplest form of a CPU scheduling algorithm. It is non-preemptive CPU scheduling, so other the process had been allocated to the CPU, it will never release the CPU until it finishes executing. So I think that's it, and thank you for listening. I hope that you will be able to solve the first come first serve problem later during our quiz. So that's it, and good day, everyone.